this video, I will be going over homework 3. We will be solving 5 problems that cover important factors in statistics. Things like probability, averages, confidence, intervals, and hypothesis tests. I am going to explain everything step by step. Let's get started. Let's begin with problem 1. It says, a basketball player makes 80% of her free throws. Suppose she takes 60 shots. So we've got a basketball player who makes 80% of her free throw and she takes 60 shots. This kind of problem is called a binomial situation. This is because there are only 2 outcomes, a make or miss. Each shot is independent and the chance of making it stays the same every time. For part 1 of this problem, it says identify the parameters of the binomial setting n, p, and 1 minus p, and explain what each represents. So, as you see here, n equals 60, which is the number of tries, p equals 0.8, which is the chance she makes 1, and 1 minus p equals 0.2, which is the chance she misses. Now let's move on to part 2 of this problem. It says compute the mean and standard deviation of the number of successful shots. Clearly explain what these numbers mean in context. The means formula is mean equals n times p. So in our case, it would be 60 times 0.8, which equals 48. That means on average she makes 48 shots out of 60. The standard deviation tells us how much her results vary. To find it, we use the formula standard deviation equals the square root of n multiplied by p, which is multiplied by 1 minus p. So plugging in our numbers should leave us with, most of the time she'll be within about 3 shots above or below 48. Now let's move on to 3, where it says check whether the normal approximation to the binomial distribution can be used here. Show the values of np and n times 1 minus p and verify that they satisfy the rule of thumb that np is greater or equal to 10 and n times 1 minus p is greater than or equal to 10. This one is pretty simple. We are checking whether the normal approximation can be used for this binomial problem. We check 2 conditions. N times p is greater than or equal to 10 and n times 1 minus p is greater or equal to 10. So here we do 60 times 0.8, which equals 48, and 60 times 0.2, which equals 12. Both are greater than 10, so the normal approximation works. Now let's move on to question 4. It says, use the normal approximation to estimate the probability that she makes at least 50 shots. Use the normal distribution with a mean of 48 and a standard deviation of 3.1. Because we are approximating a binomial distribution, we need to apply a continuity correction. Since we are finding the probability of making at least 50 shots, we subtract 0.5. So 50 minus 0.5 equals 49.5. Now we find the z-score. We do z equals 49.5 minus 48 over 3.1, which gives us 0.48. Looking up 0.48 in the z table, it gives us 0.684. To find the right tail probability, making at least 50 shots, we subtract 1 minus 0.6844, which equals 0.3156. So there is about a 31.6% chance that she makes at least 50 shots. Last question for this problem says, reflect in your own words, why do statisticians sometimes use the normal model for binomial probabilities, even though it is only an approximation? I believe they use normal models since it keeps things simple when there's a big number of trials. Even though the results aren't perfect, they're almost spot on. Now that we have went through all of problem 1, let's move on to problem 2.
It says a population has a mean of 60 and a standard deviation of 12. Sample of size equals 36 are taken. The first question asks, what is the mean and standard deviation of the sampling distribution of sample mean? The mean of sampling distribution is always equal to the population mean, so the mean would be 60. For the standard deviation, which is, in this case, is actually the standard error, we use the formula standard error equals standard deviation divided by square root of n. Here that means 12 divided by square root of 36, which equals 2, so the standard deviation is 2. Moving on to question 2, it says, what is the probability that a sample mean is greater than 63? Show all steps of your calculation, including finding the z-score. To standardize, we use the formula z equals 63 minus 60 over 2. That simplifies to 3 over 2 equals 1.5. And looking up 1.5 in the z table, it gives us 0.9332. We then subtract this value from 1 to find the upper tail probability. So 1 minus 0.9332 equals 0.0668. That means there is about a 6.7% chance that our sample mean is greater than 63. Now we can move on to question 3. Question 3 says, on a normal curve, sketch and shade the area that represents the probability found in part B. Clearly label the mean, the sample mean of 63, and the corresponding z-score. To start, we want to draw a horizontal line in a bell curve. Label the mean of 60 in the center. Next, mark the points 1, 2, and 3 standard errors above and below the mean. Then plot the sample mean of 63, which is 1.5 standard errors above the mean. Shade the area to the right of that line to represent the probability that the sample mean is greater than 63. Using the standard normal table, P of z greater than 1.5 equals 0.0668, meaning there is about a 6.7 chance the sample mean exceeds 63. This shaded area visually represents that small probability. Now for question 4, it says, explain how the central limit theorem allows you to use the normal model for sample mean even if the population distribution is not normal. The central limit theorem states that if the sample size is large enough, the sampling distribution of the sample mean will be approximately normal, even if the population itself is not normal. Since n equals 36 is greater than 30, the rule applies here. Moving on to question 5, it says, suppose the sample size increases to n equals 100. How would the standard deviation of sample mean change, and what does this mean in practical terms? If we increase the sample size to n equals 100, we calculate 12 divided by square root of 100, which equals 1.2. This gives a new standard deviation of 1.2. That means the sampling distribution becomes narrower, showing that larger samples produce more consistent averages. After finishing all the questions from problem 2, we can now move on to problem 3. It says, a random sample of 50 students has an average GPA of 3.15. Assume that the population standard deviation is 0.40. For the first part, it says, construct a 95% confidence interval for the population mean GPA. Show all steps and formulas clearly. To construct the confidence interval, we use the formula sample mean plus or minus c times standard deviation over square root of n. We plug in our values 3.15 plus or minus 1.96 times 0.4 over square root of 50. That gives us 3.5 plus or minus 0.11. When we subtract 0.11 from 3.15, we get 3.04, and when we add 0.11, we get 3.26. So our confidence interval is 3.04 and 3.26. To question 2, it says, interpret your interval in context. What does the 95% confidence level actually mean? Based off the last question, we know now that we're 95% confident that the average GPA for the entire population falls between 3.04 and 3.26. In other words, this method captures the true mean about 95% of the time. Next question. Question 3 says, on a normal curve, sketch the confidence interval centered at the sample mean. Clearly label the mean, the lower and upper bounds, and shade the region that represents plausible values for the population mean. To show this, I drew a horizontal line in a bell curve. I labeled the center as the sample mean 3.15, then marked the lower bound 3.04 and the upper bound 3.26. I shaded the area between them to show the middle 95% of possible sample means. That's our confidence interval. Now moving to question 4, it says construct a 99% confidence interval using the same data. Compare this new interval with the 95% interval. How does its width change and why? We repeat the same steps but for 99% confidence interval. Here, the z-value is 2.576. Plugging in 3.15 plus or minus 2.576 times 0.4 over square root of 50. That gives us 3.15 plus or minus 0.15. So our interval is 3.00 and 3.30. Since the interval is wider, it shows we're more confident in accounting for a wider range of possible values. Now, question 5 says, suppose the sample size is doubled to n equals 100 while the sample standard deviation remains 0.40. Recompute the 95% confidence interval and compare its width to your answer in part 1. Explain why the change occurs. Refer to the standard error. It says to increase the sample size to n equals 100. We calculate 0.4 divided by square root of 100, which equals 0.04. Then 1.96 times 0.04, which equals 0.078, which gives us a margin of error of about 0.08. Our new interval is 3.07 and 3.23. This interval is narrower, meaning our estimate is more precise and we have less uncertainty because the sample size is larger. Finally, question 6 says, in your own words, summarize how changing the confidence level and changing the sample size affect the width of a confidence interval. It asks, what happens when we use a higher confidence level or a larger sample size? Increasing the confidence level makes the interval wider. Since we're being more certain that the true mean is captured, increasing the sample size makes the interval narrower, since larger samples give more accurate and consistent results. Moving on to problem 4, it says, a soda company claims that their cans contain on average 12 ounces of soda. A consumer group suspects the mean is less. They take a random sample of 40 cans with a sample mean of 11.92 ounces. Assume that the population standard deviation is known to be 0.24 ounces. And then ask us in problem 1, state the null and alternative hypothesis clearly. Is this a one-sided or a two-sided test? Explain why. To solve this, we look at the hypothesis. The null hypothesis is that the mean equals 12, which represents the company's claim. The alternative hypothesis is that the mean is less than 12, which is what we're testing for. Because we're only checking to see if the mean is smaller, this is a one-sided test. Next, we move on to question 2, which says, compute the test statistic and find the p-value for this test. Show all steps. We first set up the z-score equation. Z equals sample mean minus hypothesized mean over standard deviation divided by square root of n. Plugging in the numbers we get, z equals 11.97 minus 12 over 0.24 divided by square root of 40. We then calculate this and get z equals negative 2.11. Looking up negative 2.11 in the z-table, we find a p-value of 0.174. Now moving to question 3, it says, at the 0.05 significance level, what is your conclusion? Write your answer in a complete sentence in context. Using a 0.5 significance level, we can see that p equals 0.0174 is less than 0.05. Because the p-value is smaller than our significance level, we reject the company's claim or the null hypothesis. There is a significant evidence that the average amount of soda is less than 12 ounces. Next question, question 4 says, on a normal curve, sketch and shade the area that represents the p-value. Clearly label the population mean, the sample mean, the test statistic, and the rejection region. Indicate whether it is a one-tailed or a two-tailed test. We will start by sketching the normal curve and marking the mean of 12 ounces in the center. Then we mark our standard errors. The standard error, which we calculated as 0.038, is shown below the curve. One standard error is marked above and 3 below the mean. Next, I marked the sample mean on the curve and indicated the corresponding z-score of negative 2.11. I shaded to the left of 11.92 to represent the p-value. Then I labeled the critical value x equals 11.9375 and shaded to the left of it to indicate the rejection region. Finally, I noted that 11.92 falls within the rejection region. Question 5 asks, conceptually, what does the p-value represent in this situation? Explain what a small p-value tells us about the evidence against the null hypothesis. The p-value represents the probability of obtaining results this extreme if the company's claim were actually true. Because our p-value is small, it indicates that these results are very unlikely under the null hypothesis. Therefore, we reject the null hypothesis. We can move on to the last problem. Problem 5 says, a nutritionist wants to test whether a new diet changes the average cholesterol level from the historical value. Hypothesis population mean equals 200 milligrams per deciliter. A random sample of N equals 15. People on the diet has a sample mean equals 194. And sampled standard deviation equals 20. Assume the population is approximately normal with no strong outliers. For the first question, it says, state the null and alternative hypotheses to test whether the diet changes the mean cholesterol level from 200 milligrams. Is this a one-sided or two-sided test? Explain briefly. For this question, the null hypothesis is that the mean does not equal 200, making this a two-sided test since the difference could be either higher or lower than 200. Next, for question 2, it says, compute the test statistic t equals sample mean minus hypothesized mean over sample standard deviation divided by square root of n and the degrees of freedom. Here is that same equation. Plugging in the numbers, t equals 194 minus 200 over 20 divided by square root of 15. This gives us approximately negative 1.16 as our test statistic. For our degrees of freedom, we just subtract 1 from n and get 14. Moving on to problem 3, it says find the critical value t for a two-sided test at a significant level of 0.05 with your degrees of freedom. Decide whether to reject or fail to reject the null hypotheses by comparing the absolute value of your t to the critical t. We use the significance level A equals 0.05 and degrees of freedom equals 14. The critical t value for a two-tailed test at this level is plus or minus 2.145. Since our absolute t value is 1.16 is less than 2.145, we fail to reject the null hypotheses. There is not enough evidence to conclude that the mean has changed from 200. On to question 4, it says, on a t-curve centered at 0, sketch and label the two critical cutoffs at plus and minus t. Mark your observed t-value and shade the two rejection regions. Clearly indicate why you observed t falls in the fail to reject region. I started by drawing a regular bell curve with the mean marked in the center. Then I added the critical values at positive 2.145 and negative 2.145 to represent the rejection regions of both tails. Then I shaded the rejection regions. Next, I plotted our test statistic, negative 1.16, on the curve to show that it falls inside the non-rejection region, meaning it is not the rejection zone. Moving to number 5, it says, construct a 95% confidence interval for the true mean using the t-star critical value. Explain how the interval supports your decision in part 4. First, we set up our equation. 194 plus or minus 2.145 times 20 over square root of 15. That equals 11.08 for a margin error. So we take 194 plus or minus 11.08, which gives us a confidence interval of 182.9 and 205.1. Since 200 falls inside this range, it supports our conclusion. For question 6, it asks us to explain how interference using the t-distribution for a population mean is similar to and different from the z-based significance test. To answer this, both the z-test and t-test compare how far a sample mean is from the hypothesized population mean. We use the t-test when the population standard deviation isn't known and when the sample size is small. The t-curve is also wider because smaller samples have more uncertainty. That completes all 5 problems. After reviewing them, I hope now you have a better grasp of these concepts. Thanks for watching.